Hi everyone! In this video done for 3 Blue 1 Browns Summer of Math Exposition, I will not teach you some already established yet surprising aspect of math, but rather make you discover some of my own thought process and how I invented quote-unquote new numbers. This is not really useful in itself and probably never will be. However, I think it is a good illustration of the creative process that has led to actual groundbreaking math discoveries. I will first explain how the real numbers are defined, then use this to build our new numbers. After that, we will explore some of their properties and go further by taking a look at how we can do the same thing based on other structures than real numbers. Also, I will not prove everything I say in this video. I will only focus on the demonstrations that help gain an insight. With that said, let's jump in. If you're at least a little used to math, you've got a pretty intuitive understanding of what real numbers are. But what's the exact definition of those numbers? Well, it's not that simple. We know what integers are. We have an easily understandable definition for rational numbers. A rational number is simply an integer divided by a non-zero integer. And from these rational numbers, we can define the real numbers, which are in a certain way an extension of rational numbers. There are multiple of these definitions, and one of them is with Cauchy sequences. The definition of a Cauchy sequence is this. I can sense that some of you haven't instantaneously understood, weirdly enough, so let me explain. A sequence is Cauchy if and only if its values become arbitrarily closer to each other. For any given distance, there is a certain point from which all the values are closer to each other than the distance. For instance, this is a Cauchy sequence. This is not. And this, well, it's not. Because although consecutive values are closer and closer, square root of n diverges to infinity, so you can't contain those values in an arbitrarily small zone. And this, it doesn't converge, so it's not Cauchy either, for the same reason. It's not very hard to show that all convergent sequences are Cauchy, and from the examples, it looks like being Cauchy and convergent are the same thing, right? Well, yes, but actually no. These properties look the same, and there's definitely a sense in which the values of a Cauchy sequence get arbitrarily close to something. It's indeed the same thing in R, which is a complete space for that reason. But it's not the case for all spaces, as a Cauchy sequence can converge towards something that is not in the set. A completely random example is Q. Square root of 2 is a famously irrational number. However, its decimal expansion is a Cauchy sequence in Q that does not converge in Q but does in R. We would like to define R by taking the limits of Cauchy sequences on Q. But because the limit in R can't be defined before R is, we do so by taking the Cauchy sequences and grouping them. We define an equivalent relation such that two sequences are equivalent if their difference is negligible, a nerdy way of saying converges to zero. Zero being rational, everything works fine. R is thus the set of Cauchy sequences in Q, quotiented, meaning grouped, by the relation. It can be seen as the set of the limits of all Cauchy sequences in Q. So, what I did is take a similar reasoning to extend the real numbers. We will use sequences on R instead of Q. That doesn't change anything because any real number has arbitrarily close rational numbers to it. We say that Q is dense in R. In that case, all Cauchy sequences are convergent and vice versa, so using them wouldn't be very interesting. Instead, we will loosen the requirements and take bounded sequences instead, which is a way broader set, because convergent implies bounded. We thus have a way broader set. You may wonder why we took bounded sequences only and not straight up all sequences, and that's for a very good reason we will see shortly after. Let's call this set H for hypernumbers. Also, we can call the limit of any bounded sequence the hypernumber corresponding to the equivalency class of the sequence, meaning its group. This is completely legal because it only extends the definition of the limit to all bounded sequences, not just convergent ones. H can then be seen as the set of the limits of all bounded sequences in R. So we just defined a set, but we would like to call it a space, aka a set with extra properties, such as internal operations. We will do so by extending the properties of real numbers seen as limits of sequences. The simplest structure we can give to this set is that of a vector space, meaning you can add, subtract, and multiply any element by a scalar, aka a real number, and the result would still be in H. For A and B in H, you can just take the bounded sequences AN and BN, whose limits are A and B. Then A plus B is simply the limit of AN plus BN. For instance, let's take the limit of -1 to the n. Let's just call it u. And 1 the limit of 1, which is also a plain old real number. We thus have u plus 1 equals the limit of -1 to the n plus 1. And of course, it doesn't matter which sequence you pick because they only differ by something negligible, so the possible sums will too. In the same way, we can define scalar multiplication by multiplying the associated sequences. It doesn't matter which sequence you pick because a scalar times something negligible is still negligible. We just made H into a vector space, how neat! But we can do more. We can also define a product in the same way. AB is the limit of AN BN. But this time it's a bit trickier to make sure everything works fine, regardless of the sequences you pick. So let's do a proper demonstration. We still have our A and B being the limits of AN and BN. Let's pick any other sequences representing A and B that we can write AN plus small o of 1 and BN plus small o of 1, with O of 1 simply meaning something negligible. Let's try to show that AN/BN has the same limit as this guy. In that case, we can develop the product and get this. By taking the limit, we see that we're left with AB and those guys. We would really like to converge to 0. But remember when we said that all sequences are bounded? That's right, a bounded sequence times a negligible sequence is still negligible. So we've just shown that the product between two hypernumbers can be defined without any problem. H is then not only a vector space, but an algebra, with the identity element being 1, the limit of the sequence 1. So, can we divide by hypernumbers? Before we answer this question and explore more properties, we need to talk about eigenvalues. Each hypernumber has a set of specific real values that dictate its properties. This stems from the fact that all bounded sequences have what we call adherent values. An adherent value of a sequence is a number which a subsequence converges to. For instance, this guy has -1 and 1 as adherent values, and the sign actually has the whole line segment -1, 1. Also, because sequences converging to a hypernumber only differ by something that converges to 0, the subsequences have the same limits, so those adherent values are the same, meaning they only depend on the hypernumber. Those who are familiar with the linear algebra might be wondering why I chose to call them eigenvalues, and you will see that they share similar properties to those of matrices. Let's also call the set of eigenvalues the spectrum, noted SP. To get back to divisibility in H, we can check if a hypernumber is invertible based on its eigenvalues. And just like with matrices, a hypernumber is invertible if and only if 0 is not an eigenvalue of it. That's because if 0 is an eigenvalue, all associated sequences have a subsequence that converge to 0. So the inverse would need to have sequences with subsequences that go to infinity and thus not be bounded. An additional property has to do with polynomials. If a polynomial evaluated on a hypernumber equals 0, then the eigenvalues of the hypernumber are contained in the polynomial's zeros. Note that the opposite isn't always true because you can add any non-eigenvalue 0 to a polynomial by multiplying it by another polynomial. For instance, u squared equals 1, so u squared minus 1 equals 0. And the eigenvalues -1 and 1 of u are indeed zeros of the polynomial x squared minus 1. However, not all hypernumbers have such polynomials. We can also use those eigenvalues to define a norm, aka a distance to 0. The norm of a hypernumber is the greatest absolute value of its eigenvalues. This simple definition validates all conditions to be a norm: homogeneity, separation, and the triangle inequality. And finally, we can define an order. We say that x is bigger than y if all the eigenvalues of x are greater than those of y. The only caveat is that this order is partial, meaning that not all hypernumbers can be compared to each other. So that's it for our hypernumbers, which are an extension of the real numbers. But what if we use the same construction on other vector spaces? Actually, things still work out. You can, for instance, take h of c and end up with the complex hypernumbers. H of c still has all properties h of r has, except for the partial order thing, but that's only because complex numbers in general can't be ordered. You can also build h over sets with less properties like vectors, for instance. And of course, the properties of h of e depend on those of e. Hell, you can build h over something that's not even a vector space. So let's sum up what we have done. We built a new algebraic structure over R, discovered some interesting properties, and then thought about building it over other types of structures. I could have given even more details and specific properties, but that's not really the point of the video, and I highly encourage you to try and explore it by yourself. You might want to ask me, why did you call those numbers? According to their original definition, they're just classes of sequences, nothing to do with numbers. And in fact, you're right. But remember that real numbers can be defined the same way. Actually, it doesn't really matter how we call them or the exact definition given to them. What's really important is the structure it has, the way numbers and, in our case, hypernumbers behave. If it looks like a duck and quacks like a duck, then it's isomorphic to a duck, and that's what's really interesting. Will that ever be useful in math? Probably not. However, I think it's the process that's really interesting there. Some pretty smart guy extended the rational numbers into the real numbers, and we extended this extension to create a new structure of our own. And it's precisely that way of thinking outside the box of trying to generalize concepts outside of their original realm and see which properties are kept or added. That leads to progress in math. That's how we discovered complex numbers, by expanding the plain old real numbers. We lose some properties and gain some. Heck, even integers are a generalization of natural numbers. And some functions used in important parts of physics or cryptography, like the gamma function or Riemann's zeta function, are generalizations to the complex plane of simpler functions. These are specific examples, but by thinking about it, you'll realize that most mathematical concepts originated the same way. We take something we already know and ask ourselves, what if? So, who said math isn't creative?